people who are signing in. We are at Field Trip Fridays, and we're going to start in just a few minutes. It's like just a little bit after 11. We're letting people sign in. Well, my phone says it is 11, so we have 50 attendees now, and we have about 100 people had signed up. So I want to introduce my co-host is going to be Dr. Richard Behl from California State University at Long Beach, and he was the field trip leader on the video we're going to show at the first part of the show, which was taken in Paradise Cove near Malibu Beach in 2015. And I also want to mention that we have a sponsor for Field Trip Fridays, Thunder Exploration. A lot of people in Houston know Walter Light. This is his personal company. And he has generously donated a significant amount of money to cover our Zoom licenses for making this program free. Well, let's get the meeting formally started. We're at 11:02. We have 66 attendees. I wanted to thank our sponsor. We'll close this down. And now we're going to come up and we're going to show a video. I'm going to stop and start it a few times, but basically we're going to get to see Welcome to Southern California.
So this was 5 years ago, and we've run this field trip again last year with some new data for the Pacific section APG meeting again. And so welcome to you all.
Okay, let's back in the mode. There we go. Okay, so this is Google Earth. I thought a good way for our people who are not from California to know where this is. I just pulled up Google Earth and put some pins in, and this map Rick provided. So this is what is Walter Pyramid and
so the Walter Pyramid is the iconic blue pyramid. That's one of only 3 large pyramids in the United States. It's our sports arena for indoor volleyball, basketball, and things like that. So this was the pathway of a bus going there from the last Pacific section APG meeting. And Paradise Cove is a beautiful beach. The access is privately controlled, although they let field trips in. And then we walked on out to something called Point Doom on this field trip.
Okay.
So it's about an hour west of downtown LA.
Okay, so now we get into real geology here. So the little red square is the end of the field trip, and there's faults, transpressional faults going right through the beach area.
Yeah, exactly. So the California mostly runs northwest, southeast along the coast, but there's a whole area here called the transverse ranges that run east-west, and they're shortening, and they've been shortening for at least the last 2 to 5 million years, depending where you are. And so you have all these thrust faults shown here. And this is what's lifted up the mountains north of Los Angeles and made all the folds that make the structures of the oil fields of Santa Barbara and Ventura. And so our field area down in Malibu is right next to one of those major east-west trending faults. It has a lot of splays through it.
And a quick strat column of the Miocene. And in the rocks, are we going to go, which one of these ages are we going to see on our field trip?
So we're going to be walking from the late to the middle Miocene, which is going through these foraminiferal stages from the Delmontian to the Monian, maybe touching down into Louisian. And this is the time frame that the Monterey Formation was deposited. But the Monterey Formation has been mostly studied and defined and thought of as entirely the fine-grained sediments, where there's a lot of sand associated with it, submarine fans and submarine channels. Then it's often called the Modelo, even though the fine-grained rocks are quite similar, but they're intercalated with sandstones.
And then in Los Angeles, they call it the Puente?
Yeah. The Puente Hills are to the east of LA where they can be exposed and they're first named, but that's what they call the same unit in the subsurface of the central LA basin.
Okay. Now this is a great stratcom that came out of your student, Nagira. Now, can you pronounce her name again?
It's Wanjira Jaguna did her master's thesis on this site, and she was Very, very lucky, except for when she occasionally had to run into protective landowners when she was getting up on the cliffs. Um, uh, and this is the section she made of that, and she broke it down into four major lithostratigraphic units. And we're going to be walking from the top down, just like drilling a well on this field trip. So we're going to start up in what we call the Cherty diatomite unit, which is mostly a diatomite or a diatomaceous mudstone, but there's these chert nodules and beds within it. Then we're going to move down into what we call the mixed clastics, which was intercalated sandstones and even debris flow deposits with those fine grain silicious mud rocks. But when you get down towards the bottom of that unit, the rocks have been more deeply buried. So now the diatomaceous sediments are starting to alter to diagenetic silica. And then they start forming rocks we call porcellanites.
Yeah, so we'll quickly go through this, but this is just sort of a diagram
Yeah,
of
so
the
the
Monterey
early part of,
Shell.
yeah, the early part of the Monterey was deposited during basin extension, so there's a lot of volcanics going on as well. So we see this sort of interfingering or intercalating with volcanics. In fact, the end of our field trip ends at a volcanic unit, which makes the resistant Point Doom sticking out into the ocean.
Okay, I think now we're getting up to the first. Oh, this is so beautiful.
So we're near Highway 1, which runs along the coast, and this is a spot where the old Highway 1 had actually been washed out by erosion, and they had to cut on through into the rocks to last Highway 93.
Okay, hold on. We got Charles wants to say we're going to turn up. Charles has got an introduction. This is my husband, Charles Sternbach. He often appears in my videos, and he often appears to give us a view.
Right, we're at Paradise Cove. So we're going to walk up section, down section. It's about a 2-mile walk. And we're near Malibu, California, and it's a really good day.
Yeah, so we've cut the sound back here because, but what Rick's warning us here, I remember what you were saying. You're warning us the surf is high, and that what is it? People have field trip. People got washed out to sea.
Yeah, so that's one thing you got to be careful about working on the beach. The beaches are great because they give you freshly eroded beach platform and cliffs to study, but you always got to pay super attention to tides. I pay more attention to tides than weather when I'm planning my field work and field trips. And in this particular trip, we had to go around a few protuberances or prominences, so we had to time it right so that as we went down section, we were chasing the tide falling. But there still were some big waves that day, so we had to watch out to make sure they didn't double up and come in and get us.
So the next scenes we're going to see are some really incredible turbidites and sandstones of this mixed clastic member.
Yeah, so it's very
Oh, here we have
interesting
one slide. We have to
this.
explain. There's some interesting sand and silica relationships here.
Okay, so just very quickly, we're primarily looking at fine grain rocks, which are made of detrital material, clay, silt, and sand. But what's unique about the Monterey and has some similarities to like the Woodford and things like that is that it's so highly siliceous. And in this case, the silica comes from diatoms, which are plankton, algae. And also we have calcite and of course a lot of organic matter. This is a source rock and reservoir also in the area. But the silica is not stable. So with burial, it dissolves and reprecipitates and turns to diagenetic silica, first as a stage called opal CT and then finally as quartz. So the ternary diagram there is just showing that you can have this range of lithologies that will be slightly different depending on the degree of diagenesis. So like a pure diatomite will turn to a chert with burial.
Wow. Okay. Back to the rocks.
The one thing to note is that the rocks, when they're fresh, unless they're highly siliceous, tend to be dark because they're organic rich. But when they get up into the cliffs where they've been weathered a little bit, they're so porous, they become very light colored. So it can be a little confusing, but if you trace the dark rocks on the beach platform up into the cliffs, you'll see they just get lighter in color.
And
So
so
these are
everyone
the
was fascinated by this big, thick tan sandstone. And would you describe this as a turbidite?
Yeah, absolutely. So here, generally the sort of tan-colored beds are the sandstones, the turbidites, and they're being deposited down into these diatomaceous muds or these diatom oozes. And you can see beautiful flame structures and rip-up clasts as we go along. And then a little bit later, I'll tell you about some of the depositional facies. But so here we are actually on the fringes of a submarine channel. So that's what makes this particular location so interesting is we're not just in deep water fine-grained sediments and we're not in a submarine fan. We're at the fringes where these two processes come together.
Well, this was really amazing. So, in this lighter color, would you say this is a diatomite? It seems to have almost flame structures underneath it.
That does have flame structures, and that is a sandstone there. It's just got a lot of salt precipitated on it to give it a light color. So beautiful flame structures here. Oh, you'll see some fantastic interformational conglomerates from the republics of the diatomaceous
Okay,
sediment.
Charles has a point here, and let me turn him up so we can see. Go.
So the sandstones are recessive because they're porous, and they're so young that they haven't had much cementation. So they recede. The sandstones are the soft part.
Yes.
Yeah, that's an interesting point here is when you're working in relatively young, uncemented sediments, the muddy ones are more cohesive, and so they're more resistant to erosion.
And this particular one is just full of cobbles. What look like the little white dots are all little pebbles and cobbles.
So you'll be noticing that some of these layers are very well laminated, and those are the hemipelagic sedimentation of these diatom-rich layers coming on down, making laminations, and then others are more massive. And here in the middle of this light-colored bed, you see all these little vertical veins or fractures. This is a unique gravitational extensional feature in siliceous sediments found all around the world of all ages from Paleozoic to very, very young.
So now we're going to look at some interesting rocks that start to get more white. They're white phosphate rich rocks.
Well, the white ones are actually very silica rich and porous and blocky and brittle, but the white layers, laminations and blebs within the dark mudstones are phosphatic. Those are in the organic rich mudstones. And here you're also seeing lenses and pigeon swell beds of cross-bedded sandstone, cross-laminated sandstone.
So the tan is sandstone.
Correct.
And then this is also sandstone?
Nope. Those are the diatomaceous mudstones still. And we're not quite down to where they're undergoing their diagenesis to the next silica phase. But that's what makes this a really interesting reservoir.
Look at that
is
fault.
we have a 3 lithophases here. Oh yeah, and the nice normal faults there. This is a 3-part depositional system that's got hemipelagic settling, got lateral transport of sand turbidites and overbank sand flows that make the rippled beds, and also gravity flows that are muddy diatomaceous sediments. And they all 3 have different porosity and permeability systems, so they can lend to a 2 or even 3-part reservoir here that's interbedded.
So most of the people in the field trip couldn't decide whether they want to look at the ocean or want to look at the rocks. We did both here. So this is an interesting slide because when you work the Gulf Coast, you never see these type of rocks this much chert. And so it's pretty foreign. Is California pretty unique in this? I think is there anywhere else that you go that can see this range of silica phases?
Yeah, actually there is, but it's California where it's been studied and produced by far the longest. So you also have siliceous rocks in Japan, in the North Sea, um, uh, uh, in India they're producing out of porcellanites and siliceous rocks. So around the world they are. They're an undertapped opportunity around most of the world. But in California we've been working on them for 100 years. But the
So
diagenesis is very important for understanding and taking advantage of the siliceous rocks.
So at this point, we're getting into a whole different color of rocks out by the beach, and they're very smooth, and they're almost like you said, almost like you can make pottery out of them.
Yeah, yeah, and we're also, depending on whether the rocks are cemented with carbonate or silica, it makes them more resistant to make those ledges that are protruding out into the sea. But as you notice, that people who have now, for the most part, removed their shoes um, as they're walking on down along the beach, so that makes it another nice nice aspect of this field trip.
There's a big sandstone there.
Yeah. As we're going to go along, you're going to start seeing more debrites. So we're getting into in sort of the lower middle part of this section where there was steep slopes and starting to be more tectonic activity. And so there was a lot of downslope transport um,
Here's
that
a
will start picking up here a little
here's a
bit.
cool sand bed here.
Yeah, yeah.
And what's happening is over our heads are very expensive houses. So if you look up on top of the cliff, people who are very wealthy are up there with they fenced off. You can see some of their dreams, and they actually have individual steps that can come down on the beach. Right? Every house has its own either elevator or steps so that the people can come down on the beach. And I don't know what they thought about us today, but they could they this is not a private beach, but they have the way to get down there and enjoy the beach right from their houses.
So in California, there is no such thing as a private beach. There can be private access to the beach, but even that is contested. Oh, these are these beautiful slope breccias where you got these massive siliceous diatomaceous rip-up clasts, sort of like a shale conglomerate, except for these are highly silica rich. But in between all the pieces, the light colored pieces of the diatomaceous laminated sediment, you get that orange sand. So this has become a mixture, almost a pudding stone of those kinds of mixed
And
clasts.
coming up, we're going to see much more deformation in the rocks, and this is beautiful. I mean, this is like cover photo type stuff, and I got pictures, and everybody got pictures. So as we come up, I mean, now each of these bands is different amounts of sand or just different colors, mineralizations.
So the darker orange is sand, porous sand, sandstone. The lightest laminated colors is diatomaceous or diatomite, and then the in-between kind of tan is a siliceous mud that was a gravity flow deposit. So we got two types of gravity flow deposits, the sand turbidites and the mud turbidites, and then we also have the hemipelagic settling laminations here.
And then this is all starting to get cut by quite a bit of the transpressional tectonics, but it looks kind of like normal faults, right? You don't
Yeah, so that's actually a really interesting thing that a lot of people don't realize in their structural understanding is that when you have thinly layered rocks and they're not at great depth and you're shortening them, not only are they folding and thrust faulting, but they also extend along their axis. And so that extension is accommodated by joints and by normal faults. So at the same time, in the same shortening regime, you get folding and thrusting, but perpendicular to that, you get extension in normal faults and joining. So it's really cool. On this beach, you can look one way, and then the beach curves a little bit, and you can look 90 degrees the other way, and you can see these two different sets of structures that seem completely incompatible, but they're actually all occurring in the same rocks at the same time.
so here we see normal faulting and like a little hint of some sort of thrust
Thrust.
faulting.
Yeah, that's right.
Wow. So I don't know what efforts made of restoring this. It sounds like an interesting exercise. I'm sure
Yeah.
it all
So
restores pretty well.
this is This is so deformed because it's close to a major fault offshore that's a thrust fault. But that thrust fault itself has multiple splays, and a little bit will be running into one of them, and a great deal of deformation associated with it. But these are one of these east-west trending faults that allowing shortening in the north-south direction across the western transverse ranges between LA and Santa Barbara. That's Wanjiro Jaguna. She's my grad student
Right.
several years ago who works for Southern California Gas now and whose thesis was on this area.
So here's some mixed class here. This is cobbles that during the deformation kind of were resedimented down into the formation. They're the same formation, just cobbled and resedimented into itself then.
Correct, correct. And you know, it's not uncommon in submarine canyons to see what people call shale conglomerates, which are erosion of the cohesive sides of a canyon and resedimenting it down within the canyon. This is like that, but different in the sense that it's all concentrated in a certain interval in the stratigraphy, and it's all made of highly siliceous muds, diatomaceous muds.
And there's some
Now
pretty
these
coarse.
clasts are really cool because these are now a distinct lithology. These are blue schists. And blue schists, if you guys remember your ancient geology, come from where you have a subduction zone that has brought rocks down deep fast but hasn't heated up, and you get these blue schists. And these were exhumed as California started to get ripped apart in the middle Miocene and brought these blue schist rocks up to the surface. And here's the marker of when that exhumation brought these deep metamorphic rocks up to the surface.
And the blue schist originates somewhere in the Nevadas, or where do the blue schists?
No, much more local. The Southern California had a major detachment in the middle Miocene. So as it converted from a subduction zone prior to the Oligocene to a transform margin, it went through a stage there where it was under transtension and being pulled apart. And that's when the basins formed. Now these are big cobbles of dolomitized sandstone and mudstone.
Just a little bit here. Oh, we'll just pass. Okay, so
There
you're
you go.
saying
There
these
you
are
go.
cobbles.
Yeah, so these have eroded out of the cliffs, but they're so big and they're so hard that they've been preferentially preserved here, whereas the rest of the rocks kind of break up and get carried away. So that in the June through July, August California, what's typical is mornings are cool on the beach because it's hot inland and that's pulled the moist marine layer in, and then it warms up and clears up by kind of mid-morning, and then we have these beautiful days that are sunny but not too hot and not too humid, being here right along the water.
This was kind of a tricky part here.
Yeah,
Okay,
yeah.
so now we're getting down into the older rocks, into some very dark rocks.
Yeah, these are into the rocks that are primary source rock, even though they're not mature here, but they're the primary source rock for the Monterey, and so they tend to be organic rich black shales, often phosphatic, and often interbedded with dolomite, which are all indicators of slow sedimentation, which tends to concentrate the organic matter.
And
What's kind of cool
look at
here,
this stuff here.
yeah,
Very organic rich.
yeah, interbedded with those very light white blocky, which are now the diagenetic siliceous rocks that we call porcellanites. And they're called that because they look like porcelain. They look like a ceramic. And the porcellanites are a reservoir many places in California because even though their permeability is low, their porosity is so high and their permeability is good enough they can produce. And then when they're fractured like this, that adds a whole nother aspect for moving the
So what's
fluids
the
through.
total organic carbon like in these dark rocks?
Oh, in this area, anywhere from about 4 to 7%.
But it's not thermally mature. You told me that in the practice session. I could not believe it. So
That's correct.
there is no oil seepage going on the beach here because these are not thermally mature.
Um, well, they're thermally mature 20 miles from here in the LA Basin, and they're thermally mature offshore about 15, 20 miles. But in this particular area, the Monterey's shallow, and it's never been deeply buried.
Wow.
So you can imagine it's not too hard to get grad students to take on a project when you have field areas like this. Now look at all the beautiful jointing in these rocks. This is where you really start getting what we call the mechanical stratigraphy of these rocks, where the porcellanites and the dolomites are highly fractured, but the mudstones and the diatomites are not, because they deform with very different styles, even if they've experienced the same strain. So they have different mechanisms of deformation: compaction, jointing, fracturing, faulting, folding.
Well, we really didn't see this silica cement earlier in the fractures, so this is sort of a new feature. All this white silica cement wasn't present in the other rocks.
This is, and you start seeing a lot of just beautiful, beautiful jointing in here. As we're heading on down the section a little farther, see, look at that. If you stop it right there for a sec, look at how the lighter colored layers have these what we call bed confined fracture sets.
Yeah.
And they're all allowing these rocks to extend horizontally to the right and the left. The finer grain rocks, that are muddier, the muddier rocks that are there, and the sandstones, which are not cemented, are just able to deform in a more ductile manner and be stretched by grain rearrangement. And so you don't see the fractures in them, although you might see some normal faults.
Ah, okay. This is one of my favorite parts. We did see a surfer, but quick, we've got a movie quiz break. Hold on. Okay. Does this movie scene look familiar? What's that? The Statue of Liberty. Well, you gotta be, I gotta tell you, anybody that wasn't born in the 60s, like I was, may not know this was the most popular film of the late 60s, and it spawned a TV show and 4 sequels. So Point Doom was actually the location of the final scene of the Planet of the Apes movie, and I'm sure you can rent it. But this was the iconic moment where Charlton Heston's astronaut character realizes he's on Earth, he's not on another planet, and he goes, "You've ruined the Earth!" Yeah, now back to geology. So there's Point Doom out here. So actually the film, you said that they went around the corner to the other side where they filmed that iconic scene. This is Point
it's
Doom
the other
here.
side. Yeah. So you see that the water is much farther out now than it was when we first started the trip. Beaches have become much broader.
Now we're excited because here we have a recumbent fold.
Now we're approaching one of the thrust fault splays of the Anacapa Doom fault system, and this is on the hanging wall side, and so the hanging wall side has been folded and thrust and highly deformed, and you see once again that the different layers, the shales and the siliceous rocks, are all deforming differently. Now, the muddy rocks here are very organic rich also. These are the organic rich ones that we were looking at a little while ago that have now been thrust up. And a very, very unusual thing happens here. So this is the footwall side. Great, thanks for stopping there. This is the footwall side. So this is where the nearly horizontal, just gently dipping beds have been folded up vertically, and the main fault runs right in that crevice there where the vegetation is on the right side. So to the right is all the highly deformed rocks that we were looking at and we will be looking at with all the tight folds, and on the left is the footwall side where it's been bent up with drag along the fault.
Okay, so Charles is saying something here. I think he's going to talk a little bit about these shales got chemically burnt, huh? Let me go back to here. Let me go start this again. Oop. Oh, I don't. Maybe he's not going to talk. I guess he might got muted. But anyhow, what is burnt shales, and did we stop here to take a look at these?
Oh, well, first of all, this is fabulous. These rocks have been naturally, spontaneously combusted, and they are, depending on how long they burned and their organic content, they go from anywhere from being just a little pink to black to many places they actually melt and they turn into a glass. And this is a natural process that occurs in organic riches that bear sulfides. So when you have sulfides like pyrrhotite, pyrite, things like that, and they get exposed by a landslide to oxygen all at once, they oxidize rapidly, and that's exothermic, and they give up a lot of heat. So if all around the world in organic rich rocks you can find burnt shale exposures, and only recently we've realized that they're most commonly associated with landslides where you get this sudden blast of oxygen to these highly reduced phases. And then I was doing some research and I learned from some friends that in even when they were building the Panama Canal and they bored their holes for the Panama Canal, that caused the rocks to get so hot that they caught on fire. And they really were a problem that had to be overcome in building the Panama Canal because it went through some organic rich Cretaceous, I believe.
Well, just to
Shales.
clear, these caught on fire like millions of years ago. They're cold now. No, when did they catch on fire?
Yeah, probably within the last 100 years.
Oh,
Yeah, and in fact, there's a well-studied case in a landfill down in Orange County, California, where there was a landslide and they measured it getting to 800 degrees C and generating hydrocarbons out of the rocks by pyrolysis and then burning those hydrocarbons right there in front of their eyes.
well, is this something that Californians are worried about? And are I know it's one of the many natural processes in Californians that worry them. Uh, and so I guess you have some public outreach to convince them the burnt shales aren't the result of something the humans are doing.
Well, you can imagine that the people with the multi-million dollar houses up on those cliffs probably don't want this to happen again.
So these rocks are very, very white now.
Yeah, so these are the porcellanites. So these are highly siliceous mudstones that are made of like 80% silica that has been recrystallized into the diagenetic form called opal CT. And just look how brittle they are. And they're interbedded with those very organic rich and slightly phosphatic shales in between. So look at the difference, the contrast in mechanical behavior there. The brittle but porous porcellanites are highly fractured with these nice joint sets, and the mudstones are almost not fractured at all because they're ductile.
Well, we've been walking all morning. I know it's been a long trip. This is getting toward the end of the trip. So we have a little longer. If you guys have any questions for Rick Behl, please go to the chat. And Rosemary or Diana are going to open up the chat for a few questions after the video's over.
There's Charles.
Yes, Point Dune.
We had about 150-foot climb to get up off the beach at the end to meet the bus, which would come to meet us. And that's the edge of Point Doom there.
And this is a surfing spot. There's some surfers out there. See the
It
little
could be a
heads?
great,
Those are not
yeah,
whales. Those are surfers.
yeah, it could be a great surfing spot. And Point Doom, as I said, is one of those middle Miocene volcanics that just makes a very resistant to erosion plug there at the point.
Okay, this is near the end. So Rosemary and Diana, do we have any questions on the chat?
Hi there. Yes, we do have a couple questions. First question comes from Greg Blake. Where is the shelf and slope that are related to the debris flow and turbidites? Any relationship to the Topanga Canyon section?
Well, hi, Greg. Good to know you're there. Well, yeah, I think so. And I actually have a figure that we didn't get in here, but this was deposited, as you would know, from the late Middle Miocene to the late Miocene, and the transverse ranges had not fully rotated to their east-west position. And so the Topanga fan was coming down from the north, north of the Santa Monica Mountains and sort of around the edge of them. Some of the sediment, a lot of the sediment went into the LA Basin proper, which would be sort of due south into the southeast. But some of it went on out to the southwest between Palos Verdes and Malibu. And so this is on the flanks of that sediment pathway, I believe. And so we're getting the sort of the overbank and the larger turbidites. Yes. So I don't know if you included, Linda, the one other figure I had that had the arrows, a whole chain of arrows on it. But
I was just trying to
yeah,
find
probably didn't get that one in there. But anyways, so yeah, if you can imagine that all of that top part that's going sort of east-west along the coast west of LA was rotated, instead of being at 9 o'clock, was down at around 7 or 8 o'clock. And so there was a more narrow pathway between the Palos Verdes Peninsula and the Malibu coast, and that's where the sand was being transported.
Well, let's take another question.
Okay, the next question actually also comes from Greg. Is the interbedded sandstone deposition related to eustatic changes or tectonic events?
Don't know for sure, but I believe it'd be tectonic in this case. We're still seeing this in sort of a very similar lithostratigraphic succession if you take out all the sand, as you see out in the coast in the Santa Barbara area. We go from a phosphatic organic rich to a calcareous silicious to a silicious sediments, and the sandstones sort of in that time period as we go from the calcareous silicious to the fully silicious, and that was not a significant sea level fall interval, I don't believe. But I'll have to think that through. I'm not sure.
Well,
sorry.
We can send Rick's email along to all the participants. Is there another question?
Yes, there is. So this one is from Eric Peterson. Did you encounter tar from seeps on the beach?
So it's actually really interesting. There's different areas where you get the tar seeps. So this Malibu coast, not very much. There's not very much known offshore seepage in this part of the LA offshore Santa Monica Basin. But if you go west about less than 20 miles, you start getting a lot of seepage up active faults breaking the surface that are being fed from deep enough Monterey that they're actively migrating and generating at the same time.
Well, where they still have off of Ventura, right? We took a boat trip out to the existing Ventura platform out there, and obviously there was oil coming up. We could see it on the boat. So, but not here on this particular place.
Not here. But if you were, but if you go back onto the other side, onto land, there's active seepage in the famous La Brea tar pits, right? And that's coming up from faults above the Salt Creek oil field.
Wow. How about any more questions?
Yep, there's just a few more. So here's one from Jim Robertson. Whatever became of Chevron's Point Arguello discovery and subsequent production from the Monterey?
Point Arguello was sold to actually a series of successor companies. Arguello had been operating. I think it is now shut in, but it had been operating until just a few years ago. There had been an opportunity before the big Gulf blowout was a grand deal with the state of California and local environmental organization stuff to let them do some extended reach drilling in the state waters for a 10-year period of time and really tap an untapped reservoir there. But then that all got shut down when we had the big BP blowout in the Gulf because everyone got gun shy. Right now, unfortunately, the offshore in the Santa Barbara and at Point Conception has been greatly impacted by a pipeline leakage that occurred a few years ago that has not been repaired as of yet. And so therefore the production from those offshore fields got shut in.
Okay, how about one more question?
Oh, you're going to make me pick.
Oh.
There's several other questions in here. I guess we can forward those to Rick and maybe Rick can share his email so that people can follow up with them. I'll just take the next one that was in the line. Can you briefly explain flame structures?
Yeah, sure. Flame structures are deformation of a water-saturated, muddy substrate when all of a sudden you put a lot of weight on them with a sudden deposition of sand or conglomerate. And so you put this dense, heavy material on a squishy mud, and it doesn't support it evenly. So a lot of it goes down and some of it squirts up, and the squirting up is what makes the flame. So it's evidence of rapid deposition on a water-saturated, muddy substrate.
Well, at this point, we're a couple minutes left. I've got a short video about Nova Scotia, and when I made up the original thought, I thought I had to get more time because I didn't know Rick was going to be able to join us, and I know how much we were getting into it. So I want to thank Rick for coming in from California and giving us a really great background talk. And I know everybody enjoyed it, so we will share feedback and the emails, and it sounds like some people have some awful good technical questions that you might want to follow up on. But let's just take a moment here.
I just typed my email into the chat.
Oh, great. Well, let's just, because I promised this in the advertising and it's worthwhile, let's take a short trip to another beach. It's the Bay of Fundy in Nova Scotia. And Charles and I went on this field trip. It wasn't an AEPG field trip. It was called the Conjugate Margins. And it's a partnership between two sides of the Atlantic to look at their joint rocks. And they were going to go to Morocco. And now this particular one was held in Halifax, Canada, organized by Dr. Grant Wack, who is a member of AEPG, and he's at Dalhousie University. So this is Maine. Oops, let me go back here for a second, just to set the scene. Many people have been to Bay of Fundy in the U.S. This is Maine. We flew into Nova Scotia. Halifax is on the Atlantic side, but the field trip we're going to look at is on this arm of the Bay of Fundy. And I believe Charles gives us an update coming up here. Oh, here he is. Very pebbly beach, but beautiful. And the tides are out, as you know, in the Bay of Fundy, has very, very big tides. And Dr. Wack planned this trip.
So we're here at the 5I.
So he planned this trip 2 years in advance because he knew what the tide schedule would be on a Sunday. And he told us he looked at the tide schedules and when would they be out in the morning on a Sunday, and they planned the whole trip around that. So let's see here. Charles is going to give us an introduction.
So we're here at the 5 Islands. We're on one of the arms of the Bay of Fundy, the Minas Bay, and we're looking at rift-filled deposits today. So we're going to see lake infill, and we're going to look, it's mostly Jurassic, Cinemurian, and Valanginian. We're looking at how the infill is happening, and then we're going to see basalt. So this is an area where the Atlantic Ocean could have opened up. It's part of what some people think is a failed arm, a possible opening of the Atlantic that then didn't happen, and that the major opening of the Atlantic Ocean happened farther to the east. But there are rifts and volcanism associated with that, and we're going to see those things here on a beautiful Sunday morning.
And so we had a lot of students with us, both YPs and students. They're fascinated by this rock. Initially, they thought it was a limestone.
It looks like pisolite.
And Charles thought, oh, it's carbonate, but it's actually a vesicular basalt, because you'll see later on in the show the place is cut by basalts. But these are Jurassic fluvial sandstones, a nice bright pink with some interesting glacier structures deposited in shallow water, with a little bit of phosphate on the edge here. Charles, did you want to make any comments? No, you're usually.
Finer grained fluvial systems. You can see by the grain size.
Here he is. Here's Charles.
Is that
And so here we see the first high angle crossbeds of the Jurassic rocks. And later on, as we get further down the beach, you'll see. So these are going to grade into playa deposits and Aeolian deposits. And yet this is not in the middle of Utah or in the Grand Canyon. This is on the coast of Canada.
just how much energy is taken?
So you can see that they had picked the first time to walk out at the maximum low tide of Bay of Fundy. Now here's the volcanics. So just remembering from the guidebook, and I'm not the expert that Dr. Wack is, but it's Jurassic age intrusive basalt, and it has clast that has fallen back into the basalt. So that's what we're looking at here. And so the Jurassic basalt has intruded into Jurassic sediments. And this is part of the opening of the Atlantic. You know, all the plates are separating, forming the early Atlantic Ocean. You know, that really gets going in the Mesozoic. It extends all the way through the Cretaceous. And so that's what's causing those basalts to intrude into the Jurassic fluvial system. Some pretty nice, I think, uninhabited islands there offshore. And now we're walking up to the top of an old volcanic cone where Dr. Wack's going to give us a little bit of a talk. But this was kind of rough going walking on these cobbles. We're all wearing boots, and I eventually figured out it was better to go walk in the water than walk on the cobbles. It took me a little while to figure that out. So here's Dr. Wack's going to talk about the intrusion of the. So this is an old neck of a volcano here, and we're just taking a break, looking at it. And I think as we turn to the next slide, Charles is you're going to see one of the features of basalt when it cools slowly is it turns into columnar basalt. So I think in the next shot we get to see it in columns, and then this is a little bit of deformation associated with the basalt as well. The Minas fault goes through this area, and so that deformed the basalt. But all this is happening in a relatively short period of closely adjacent time.
Then next, we're going to continue along through the columnar formation, which is the uppermost Triassic unit. Right across the bay is the other side of the rift. So remember, we're in the eastern part of the rift here, the Hoff Robin, and if thinking about the wolf focused on the other side, there's some brilliant deposits of brain channel succession. And then you have...
Guess you really can't hear what he's saying there, so let's just fast forward. Oh, here's the columnar basalt. Let's go right here. And then I remember this part, you know, there's a contact where the basalt is intruded up against the Jurassic, and there isn't really any heat contact. It was hot, but it just didn't even really, there's no heat deformation on the contact, which some people would think with such a hot lava, you know, it would have cooked the rock next to it. But it actually, there's a part where we go up and look at it, and it doesn't even cook the rock. And so now we're going to walk away from the volcanic neck and go down to see some more red beds. There's the columnar basalt. Okay, so that you can see, like, this is the contact between basalt, and then, you know, I guess this is more faulted basalt, and then we're going to walk into where the Jurassic is. Okay, now we're into the Jurassic. Actually, it says Uppermost Triassic Aeolian sand deposits. This is called the Redhead Formation, and you know, you would think if I showed you a picture of this that we would be out there in Arizona, looking at their Mesozoic rocks. And I've also seen rocks like this over in England. Of course, their Triassic is very similar because the Triassic was deposited before the Atlantic Ocean opened up. But this is just a beautiful place to take some pictures, and we ended up having lunch here. And they call this the Head Sandstone, and it's Upper Triassic in age. Here we go. So it's definitely got some really, really photo-worthy pictures here. And what was interesting, I think I get a zoom in, is you can see the bed sets really well. This is like deposited by wind blowing back and forth. So it's hard to imagine. Back in the Triassic, there was just like a Sahara desert of dunes that stretched from, Canada over to England, and of course down parts of the northeast. Even New Jersey has some Triassic sediments. It's, I guess sets the record for the widest extent of dune sands in the rock record is the Triassic. So this was at the end of the trip. Everybody's kind of relaxing. We took all morning to walk down here. So we got some final shots of like the crust beds here in the cave. Actually, this gets totally cut off from, he was very aware of the tides as we walk back. And in the final shots, you see the tides are coming in because the water goes up about 5 feet high in here at the high point of the tides. And you've got to be off the beach. I would be pretty unlikely you could climb out. So he said they had rescued people by boat who get stranded in here. So he was watching his time real quickly, but we didn't make the whole field trip and get back out before this area got flooded after lunch. Here, somebody even wrote their name in the wall there. He's getting ready for his photos. Charles likes to wear his t-shirt that says "Never Stop Exploring," and we all wore hard hats during this trip in case any loose rocks came down from the top. Now that's pretty cool. Look at this termination right here of the beds coming down, and you can walk around and get a nice three-dimensional look at it too. And we're just going to close out here. I guess, are there any chat questions that we want to follow up on? Yeah, go ahead. Why don't we just take those questions if we don't have questions on, oops, I did have very nice lobsters here at the end, so the lobsters were good. So